Anybody has questions? No. Okay, so we'll start with just a very brief review from what we were doing last time. So we are looking at essentially tools, and in there I introduced you last time to LAMPS, which is a open source software. And here you can see that I hope some of you are able to go to this website and look at it. But you can, the main point is that you can download it for free. There's an excellent manual that you can use to understand how to use this thing. And I very briefly showed you that, okay, if you want to do some problem, there are just a few commands that you need to put down, and this defines the problem for lamps. So by looking at these commands, lamps knows what you want to do, and really in addition to this, the only thing you need is this input data file, which gives the initial positions and velocities of the particles. One of the things is, of course, here when I showed you the code for soft particle method, we use the Euler method and a predictor corrector time step. In lamps, what is used is there is a Verlet method for integration. That's what is called run style. And I'll just explain to you what that is. So that's just an improvement over Euler method to calculate the next time and the position at the next time and the velocity at the next time. And this I'll just show you the formula for that. And so this was a script for a very simple problem, which is just exactly what we did for the hard particle case and the soft particle case. And we saw how these two particles can collide. And so we looked at the first example where there's this box one, and we looked at this and this GNU plot and Ovito. So if we run this, we just see that two particles in the old nomenclature 18 and 19, how they collide. And we saw that there's a close, it looks exactly like what we have done before. And then the second example also was something that we had done before. We did one demo with elastic particles. In this, if we want particles to be elastic, then our Gn, which is equivalent to kV in our notes, this should be 0. And when we do that, we saw that the system conserves kinetic energy. When we do the demo with a coefficient of restitution of 0.9, then the particles lose kinetic energy. And this RS box is the same as box, but it's a restart, and I'll show you that. And then if you have gravity, then the particles settle down. And today I want to basically look at one more example which involves flow. And so how we can do the flow, how we can do the restart and so forth. And the basic problem is flow of inelastic particles on a rough inclined plane with periodic boundary conditions, and then using another program to analyze the data from lamps. So this is what we want to do today. And so let me just go back to this. I'll essentially do some small derivation like things. So the first thing is, of course, I mentioned this velocity Verlet scheme, and this one is a way of integrating the governing equations with respect to time. So you'll remember that the Euler scheme, in that we saw that x at time t plus dt, this was just given as x of t plus v of t into dt. So this was the Euler scheme. And in the velocity Verlet, there is a correction to this. So you take the acceleration also into account. So you can write half of a of t into dt squared. So you essentially add this additional term, and that's like gives you a more accurate value for x of t plus dt. And if you look at v of t plus dt, then here also there is a small correction. So if you remember, in the Euler scheme, we had just v of t plus a of t times dt. So this was what was the Euler scheme. But here we make a small correction and we actually write the acceleration to be the average of the acceleration at time t and the acceleration at time t plus dt multiplied by dt. So if you look at this, the velocity Verlet has a one additional term. So in many of the cases, it is possible to calculate it, but when we do this calculation, if a depends only on x, then it's okay. Otherwise, what you have to do, that when you look at this, what is acceleration? Just to remind you, this is just equal to g, acceleration due to gravity, plus 1 by m sigma Fij, that is the forces, sum of the forces, j going from 1 to the number of neighbors. So this is what is the acceleration. Now we know that Fij in the simplest case is just equal to kx into alpha minus kv into alpha dot into nij, where nij is the unit normal along the particle. So this is what it's equal to. So you can clearly see that this depends only on x, because it is just xi so alpha is just equal to 1 minus the absolute value of xi minus xj, that is the distance between the particles. And this, of course, instead of alpha dot, I should just write it as Vn. This is what we had written, and Vn is just equal to Vi minus Vj dotted with Nij, where Nij is just equal to xi minus xj divided by its magnitude. Okay, so you can see this, that the acceleration depends on both position and velocity. So if you want to calculate the acceleration, so the acceleration at t plus dt, in general, we can write it as acceleration at x of t plus dt and v of t. So this is, so when we're calculating the acceleration, we'll have to use the previous value of the velocity and the current value of the position. And this is what is used in the velocity Verlet scale. Okay, I just wanted to clarify this a little bit. Now let's go to the problem that we want to study, and that is the flow down an inclined plane. And this is for our example number 3. So if you see this, what we want to actually solve for is that we have an inclined plane which is actually made up of some particles which are stationary. Let's say this is the horizontal line, and we can say this is the angle, that angle theta, whatever you want to call this. And then on top of this, we have our flowing layer. So, we are just looking at a part of the flowing layer, and our gravity acts in this direction. And there are particles over here that are flowing. So you have an inclined plane and particles are flowing under gravity. Okay. So this is the problem we want to solve. We can actually just, in our coordinate system, we can essentially change this system to something like this, that the particles are on a horizontal plane, that and then you have this layer like this, and then these are particles here, so instead of tilting the surface, it may be easier for us to simply tilt gravity. So we can imagine that gravity is at an angle theta. So we saw this last time. So as far as the particles are concerned, there is one component of gravity in the flow direction, that is, let's call this direction as x, and let's call this direction as z. So you'll have this. So this is one thing that we'll do, and we saw in the last class that it's really easy to change the direction of gravity, and I showed you what happens in our the particle settling under gravity. What happens? And then because of gravity there is flow in this direction. Now one of the things that we will use here That is, if we look at these two surfaces, we will use periodic boundary condition on these surfaces. So what are periodic boundary conditions? So these are such, you can imagine that if you have any system, and let's say if these two are periodic boundaries, then what it means is that this boundary is essentially joined to this one. And so if you're looking at a two-dimensional system, you can imagine as if you have turned this flat surface into a cylinder, and that these two edges are just joined. But from a practical viewpoint, even for a 3D system, what you have is that if a particle is here and let's say it goes out like this, then that is the same as if the particle was over here and it's coming in here. So there is, you can imagine that there is an exact copy of this box before, including all the particles, and then there is an exact copy of this over here. So in fact, when this particle goes out of here, it will simply come back in from here. So in this way, it's a periodic condition. But also what you have to imagine is that, let's say if there is a particle over here now, let's say there's a particle here, then you have to see that this particle can actually, that this particle can actually collide with this one as it goes out of here and comes in from here. So when you're calculating the neighbors, you not only have to calculate the neighbors in here, but you have to also calculate the neighbors just outside the periodic boundary condition. So the basic point is that particles leaving one boundary enter from the other with the same velocity. So it's as if, as if this surface is the same as that one. And why would you want to do this? Because it just mimics a much larger system. So you don't have bound ends. There are no end effects if you have periodic boundary condition. But of course, we need to look for neighbors across periodic boundaries. Because as this is going out from this side, it's going to start colliding with the, as this is going out from this side, it's going to start colliding with neighbors over here. So all those things have to be taken care of. Now, what this type of computation does is actually it gives us the velocity, position, rotational velocity, and so forth of every particle in the system. And we really want to know so much information. I mean, it's not of much use to us to know all that. So though you compute everything, and you need to compute it if you want to really do an accurate simulation, in the end, what you really want is you want some sort of average. And so you can compute averages And this method is also called, it's often called also coarse graining. So you're not interested in the velocity of every particle, but let's say you want to know the average velocity. Now, let's say if we are looking at a system like this one, and we assume that in the x direction there is no variation, that is, everything is the same in the x direction, and there's variation only in the z direction, then what we can do is we can actually divide our system. Let's say this is our system. We can actually just divide this up into smaller volumes. Okay. And let's call this is, let's say, dz. This, of course, as before, is z. This is x. And these are bins, or so let's say we have n bins. So there's no variation in x direction. We calculate the z variation of various things like velocity and so forth. So how would you do this? Well, we can do it exactly what we had done before. So we can just bin every particle based on its z position. And how would you do it? So let's say this is bin j. Then to calculate which bin it is in, so j is just going to be equal to trunk of z divided by dz plus 1. So you can see if the value of z is between 0 and dz, then this value will be less than 1 when you take the trunk. When you truncate it, this will be 0, and so it will be in the first bin. If your value of z is between dz and 2dz, then this will give you 1. So 1 plus 1 will give you 2. So in this way, it's very easy for every particle to put it into a bin. And then you can, let's say, calculate the average velocity in the bin. We'll call that as Vx. So the velocity in bin j is just going to be equal to, we have to calculate the average, so we just take it as the velocity in j plus Cx I, where I is the particle number. So let's call this as Zi over here. J is the bin number. So you can see this. And so this is for each particle I, we have to do this. But we also want to keep track of how many particles there are in each bin. So n of j is just equal to n of j plus 1. And then when you want to calculate the mean velocity, so this is actually calculating the sum of the total. This is the total velocity in the bin. So the mean velocity Vxj is just going to be the sum which we have just calculated divided by the number of particles. So this will be the mean velocity. And of course, this velocity, the mean position, is z of j, which is equal to z minus 0.5 times dj z. So that actually corresponds to the middle of every bin. That is the mean position. And of course, you can also calculate the volume fraction, or you can say number density if you want. Where V is the volume of the bin. So this way we can get profiles. So now you have got Vx versus Z and N versus Z. So N is the number per unit volume, V is the average velocity, and Z is the position. So this is one of the things. You can also compute stresses. So we know velocities, but we also need to know what are the stresses at every point. And there are two types of stresses. One is called the streaming stress. This is the momentum transfer due to the velocity fluctuations. And we call that as sigma s. This is simply given by minus 1 by v, sigma I going from 1 to n, where n is the number of particles. I call it as np, number of particles, into mass of the particle times ui. So where ui, which is just equal to c of I minus the mean velocity v, is the fluctuation velocity. So this is the random fluctuation from the mean value. And then there's something called the contact stress. So this is the stress transfer. There's a momentum transfer because of particle-particle interactions. And this we'll call as sigma of C. This is just minus of 1 by V sigma over all contacts of Fij times Xij, where Xij is just equal to Xi minus Xj. So this is what is known as the contact stress. So if two particles are touching, then Fij will be non-zero, and you sum up over all the contacts inside the bin. And V is of course the volume of the bin. So in this way we can calculate everything. Once we know the velocities and the forces and so forth, we can calculate the stresses, the mean velocity and everything. So you can get a full characterization. Now in lamps also, we can calculate the stresses. So it will do that for you if you just put a simple command. And the lamps command is compute. And then the identity of the compute. Now this can be anything. You can put it as 1, 2, 3, or any letter. Or so I'm going to say compute S, let's say. So that's the name of the compute command. I can call it as stress also, compute stress. But I can even leave it as S. So I'll just say S over here, compute S. But you can call it by anything. And what should we compute it for? So this is for all particles. And what do you want to compute? You have to compute stress per atom. So this is the command. And then if your thing depends on the temperature, then you should put in temperature here. But we, for all our calculations, we simply put null, so it doesn't depend on anything more. And if you put this command in, then LAMMPS will calculate a matrix which gives you the stress components and these are going to be put in a matrix called C underscore S. If I had called this by str, then it will be C underscore str. If I had called it C1, then it will be C of 1. And there are 6 components. So this I goes from 1 to right up to 6. And they are the 6 components. So C CS1 gives you sigma XX, CS2, not sigma S. CS2 gives you sigma YY and CS3 gives you sigma ZZ. Then CS4, that gives you, these are the 3 normal stresses, will give you sigma XY, CS5 will give you sigma XZ, and CS6 will give you sigma YZ. So these are the 6 components of the stress tensor. In general, the stress tensor is symmetric. So instead of 9, you have only 6. But the thing to remember is that C of S, this gives you the per atom stress. So this is the stress per atom. So if you actually want to calculate, let's say sigma XX, then this is equal to 1 by V sigma over NP CS of 1, sorry, CS I'm writing, it's actually C underscore S. C underscore S of 1. And so this is a sum of where NP is the number of particles in the bin. And V is of course volume of the bin. So you have to sum over all these stresses and then, so you'll get exactly, you'll get both this plus this. If you only want this part of it, then you can add, there are options. You can put in over here KE, then you'll get only the streaming stress. If you put, let's say instead of KE, if you put pair, then you will only get the contact stress and so forth. So you have a lot of control in doing that. So this is essentially what I wanted to give as a background for our example number 3. And so now let's just go to that. And so what I want to next discuss is the script file. And this is the script file for it. Now, if you compare this script to what we had done earlier, what are the differences? And those are marked in red. So one difference is we had in the previous thing we had FFF, but now we want to have periodic boundary condition in the X direction as we saw before. So that's why that F is changed to P. Everything remains the same. But now, we have two types of particles. If you remember, there are the base particles which are static, and then there are the moving particles on top. So that's why I make the same box as before, 0, 20, 0, 1, 0, 20. But now I want to have two types of particles. That's why I put here 2 times box. And then I have two read data commands. One is the same one as before. So I have Poswell data. This is the position and velocity data. Add append, and I'm going to call these particles, I'm going to call them as mobile particles. So then I say group mobile. So this inputs all the positions and velocities of those particles. And then I read another file called base.data, and I'll append this data, and I'll call this group of particles as static. You can call them by anything. I can call this as group 5 and this as group 6, or whatever you want to call it. You can call it by anything. But this is easy because mobile means they're the ones moving and static means they're the ones that don't move. This is the same as before. Time step is the same as before. In the Y, now I've removed, here I should have put it in. I've removed the X, the reflective boundary condition in the X direction, but I keep the Y and Z reflection. And this is also modified. Earlier we had fix to all NVE sphere. So this essentially tells us how to integrate the equations, and it says keep the number, volume and energy constant, and these are spheres that we are integrating. But last time we had all over here, that means all the particles were involved, but now we only do mobile. So what happens when you do this is the static particles position simply does not change. It is never updated. So they remain exactly where they are. And so that's why you can have in the same system some particles which are stationary and some which are moving. Then gravity we have here. So this is how we did. So we have chosen a vector which is 0.2 and -1. These are the two components of the gravity in the X and Z direction. Dump all this and go on. And then there is when I write at the end, I've got this command which says write restart, and there's a file name. So this is very useful because I can run this program for, let's say this is for 200,000 steps, and at the end of it there will be a restart file which is written. Then I can have another program which will read. We don't need to do all this again, but it can read this file and then continue the simulation from this point onwards. So it will go from 200,001 step onwards. So you can do that. Okay. So let's see now if I can show you a demo of that. And I shall go to that particular example. So I shall share my entire screen. Okay, I hope you can see it. Okay. So we are trying to essentially solve this problem. And there is a program called Flow. I think this is the one that I showed you. So here it is PFF box toolbox, then read both the data sets. This is the pair style, which specifies the forces acting between the particles, the time step, the reflect only in the y and z direction, integrate only for the mobile particles, the gravitational vector, then write the velocity and positions. And then of course this run using the Verlet integration method for 200,000 time steps, and then write the restart file. And then if I want to run it again, then I can just use another program. This is the same thing, flow, but now instead of reading all the other stuff, I'm going to read restart file. This is what I had written in the previous program. Define the region, define the pair style, time step, reflection, integrate only the mobile particles, gravity vector, dump files, that is write the data x, y, z, vx, vy, vz, and then you're done. So this way we can keep on running it over and over again as much as we want. And so let's see. So this is what we want to do. So there are a series of steps that I'll just execute this file called run, which will write. Okay, before I do that, let me just show you this file called ini.c. So this is the same as the file we used before to generate the pausewell.data, and but it will have one more set of commands. So the first part of the file is exactly the same as before, and there's this pausewell data which it writes. And then there is another part of the program in where it writes the base data. So in the same way we can do it. Now to make a rough base, what we do is that the z component of the velocity we take to be, z component of the position we take to be a random number. So this random number goes between 0 and 1. So the positions of the particles are random. So if I just do clean, then it deletes all the data files. Then I'll compile the initialization file and then I run it. So now it generates two files. One is called base data and the other is this position and velocity.data. So now we can open this using Obito. And so you can see what the base looks like. There are these blue particles and their Z position is sort of random. And this is a box of thickness 1 and length and height of 20 by 20. There are 20 particles here. And the diameter of the particle is 1. And these are the different views of that. And we can also look at what is this position velocity data. I can just add to the scene and you'll see that this is what we had in many of the problems we looked at, this uniform distribution of particles. But you can look at their velocities and you see that the x velocities of these particles are all random. They vary between -2 to +2. So yellow is +2 and black or gray, purple, dark purple is -2. So you have this. So the initial velocities are random and they're there. Now what we can do is we can run this. I mean, one way of doing it is MPI run minus NP4 LMP underscore MPI minus in, and the name of that program is flow R. Let's see if this runs. So it's giving us the kinetic energy and everything. So that has been done. Now, if we want, we can simply look at the data has been stored in this directory temp. So we can go to our Ovito and yeah, so this, go to this, and again I'll add the modification, color coding, and you see this. See how the particles, you can see that they're starting to flow. And you can also see that at the bottom the velocities are low, and at the top the velocities are quite high. And so this, of course, this is replaying it, so that's what it does. And then if I want to run it again, so instead of the same program, I'll run it and I'll say restart the flow. So because I may think that, okay, the system has not yet reached steady state. So let me do it again. And so if I do it, it will just add on. So you start from the beginning, but the new files will simply be added on to the. So now instead of going from 0 to 200, which was the last time, now it's going from 0 to 400. I can just click on adjust range and then it'll adjust the maximum minimum velocity every time. So we have already seen all this. And once it crosses 200, then that is the new data. Okay. So you can see that, normally to do this kind of calculation would have taken us months to write the code, debug it and all. But here you write, a few lines and you can immediately get the. Now what we'd like to do is, of course, take the averages and so forth. So let me just run this script, which is basically what I did right now, but it just does all the calculations again. But it will show us this is how the kinetic energy changes with time. And so you can see that initially there is a sharp spike because the particles are falling under gravity. And then slowly it reaches by the time you reach 2 seconds, the flow has reached steady state and the kinetic energy is nearly constant. So this is one way of seeing that. Where did I get the kinetic energy from? Well, the kinetic energy is written in log.lamps. So you can see This is the step number and this is the kinetic energy. And so to plot it, what I do is in this, I have a command which just copies this log.lamps to t.dat, which is a new file, and then it deletes all the data up to that line, and so I can plot it. Okay. Then there is another thing I can do, and that is restart run. Well, so this does the same thing what I did earlier. So rs run. So it starts from where we stopped, and now you can see that it has actually not reached steady state earlier, but now it's probably at steady state. So there was still a transient going on, and it slowly comes to a steady state. Let's see if we run it again, what happens. Now this is going up to 600,000 time steps, and now you can see that it's roughly constant after okay. And now to analyze this data, what we need to do is we need to read these files and read the data from these files and then calculate an average. And this is done in this program called c.cg.d. So, you know, it essentially, this is all programming in C. So the first thing is that it creates a character variable called fn, in which the output file name is created. So the character name is like this, and these x's are replaced by integer values that are calculated over here: i4, i3, i2, i1. So it starts with 0, 0, 0, 0, 0, and then it adds on to 1, 2, 3, 4, and so forth, so that every file is read in sequence. Then once you read the file, then you find out, like we did before, what is this is j. So that is just the truncate z by dz plus 1. And then if that value lies between in the region of interest between 0 and ni, then this is n becomes 1 and u also u plus 1. And then here, we calculate not only the mean velocity but also the standard deviation of the velocity. And this is the mean number fraction and the standard deviation. And then you open a file and then write down these things. I don't know if this is done already or. Okay, so there's another program called run CG here, which actually does everything. Let's see if it works out. So it will actually run the it runs the thing couple of times. That's, I guess, 3 times it runs it. This is we saw this graph. This is the kinetic energy curve. Okay, it's running it more. And that's it. So this is the plot of the number fraction, or the volume fraction, you can say, volume fraction, sorry, as a function of height. Z is the height. This is the volume fraction, F. And you can see it's around a volume fraction of 0.5. And these error bars, they give you the standard error that is calculated. So this is the sort of uncertainty in the calculation, but you can see this is about 12 particle diameters thick. And This is what the velocity profile looks like. So this is the velocity profile, and it's nearly zero. It's zero at the base, and then it increases almost linearly to a maximum value. And these small things are the error bar. So it's very, very accurate calculation of the velocity profile. Okay. So again, I will put all of these on Moodle, and I'd like you to have a look at them. So did anyone try and download LAMPS? Nikita, I know you have done it.
Yes, sir.
So you don't count because you did it before, but has anyone else tried? So no one has tried to download it.
I installed it.
Sorry?
I installed it, downloaded it.
You have already installed it? I think I would encourage each one of you to try. And, if you face any issues, just let me know or let Niladri know. He is also an expert in this.
Sir, I installed, but did not use too much. Actually, I learning these lamps.
You have installed already. Very
Yeah,
good.
yeah.
Can you try and run some of the example programs that I have put up there on Moodle?
I will try.
Okay. So I think that this is going to be. Second question I wanted to ask you is: have you seen all the groups?
I've seen my group is 6.
Okay. So please go to Moodle and just check.
Yeah.
Make sure you're in some group or the other, and you're in the correct group that you wanted to be in.
Okay, sir.
Okay. So with that, I'll end, and I'll see you now on Thursday.